Okay. So before I proceed, let me underline that the purpose of this talk is first of all to present our effort to the operational community and ask for your feedback regarding details that we may have missed or ways that we can use to make Periscope more useful for you, and technical insights regarding the rate limits, the usage statistics, or historical data on Looking Glass utilization. And generally, we want to encourage the engagement of the community and the contribution of the community to this project, because we believe that ultimately it will be successful only if it is useful to operators who provide the underlay infrastructure on top of which Periscope runs. So the high-level goal of Periscope is to provide a uniform API through which we will unify the querying and discovery of Looking Glasses that are having disparate interfaces. We are aware that this is a paradigm shift from the existing practice of querying Looking Glasses, which is basically manual. And in order to avoid conflicts between what we're doing with Periscope and what may be the intended purpose of Looking Glasses, we have built Periscope with three key principles in mind. First of all, Periscope respects the resource limitations and preserves the conservative query rates that Looking Glasses are designed to support. Periscope provides transparency and accountability for all the queries that originate from its infrastructure. And we strive to be responsive and compliant with all the requests from operators and especially from Looking Glass providers. We believe that Periscope combines a number of benefits both for operators and researchers. First of all, it provides an easy way to discover and query remote vantage points in order to obtain reverse paths. This is an essential part of troubleshooting network problems, so Periscope can significantly improve the monitoring and diagnostic capabilities that we currently have. Toward the end of this presentation, I have some case studies that illustrate this promise. Also, it provides an access control layer that makes it easy to police the usage of Looking Glass resources and prevent abuse. And by having a bird's eye view of the queries across users and across Looking Glasses, we can implement measurement intelligence that can lead to improved utilization of the Looking Glass resources and a better distribution of the query load. And lastly, we can avoid redundant queries by capturing and making publicly available historical data so that we can provide to the users the ability to consume already completed measurements on top of the ability to create new measurements. So, as you probably all know, a Looking Glass is a web interface to a router or a server that allows the execution of non-privileged networking commands, mainly for the purpose of network diagnostics. And because Looking Glasses are among the very few tools that provide direct interfaces to routers, they combine an array of advantages that are not found in other platforms. So first of all, they allow access to non-transitive BGP attributes, such as local preference values. These attributes are not possible to be obtained through other BGP data collection tools, such as, for example, route views, route collectors. Looking Glasses offer collocated BGP and traceroute monitors on the same router, so it's easy to combine both control plane and data plane routing views without having to worry about using disjoint platforms. And they also host monitors inside critical internet infrastructure, so in contrast to other efforts that crowdsource the deployment of measurement agents at the edge of the network, Looking Glasses provide a view from the core of the network, which is rare these days. And finally, quite often looking glasses are hosted in AESs that are not covered at all by other platforms, so they can extend the topology that we can observe. As a result, they have been used widely among researchers and among the operational community. If someone does a quick search in mailing lists and user forums, it's easy to find a lot of cases where operators and users try to figure out routing problems and share routing data that are extracted from looking glasses. However, looking glasses lack a number of important features that prevent their systematic and their consistent use. So first of all, they do not have the necessary standardization for input parameter and output formats. So it's very difficult to coordinate measurements across different looking glasses. In many cases, it is even difficult to discover which are the available looking glasses and in which location and with what capabilities, because there is no index that describes all these features. And there is no repository that is publicly accessible with historical measurements, so potentially we lose a lot of valuable reusable data. And finally, looking glasses tend to have very high attrition rates. They tend to be unstable, so it's hard to maintain a fresh list of looking glasses. And these are the list of challenges that we try to tackle through Periscope. By implementing a common querying scheme and by implementing the missing indexing and data persistence features. So here we see a typical Periscope workflow. As you can see, Periscope sits in the middle between the users and the looking glasses. And it is implemented as an overlay so that the looking glass deployments do not have to change at all in order to support Periscope. And the users have just to interact with Periscope and not with the underlay looking glasses. So when a user wants to create a new measurement, it is necessary to understand only the syntax of the Periscope API, which is uniform across looking glasses. And it's the responsibility of Periscope to translate this uniform syntax to the format expected by each individual looking glass. Now, when a looking glass receives a query, it will process it, and usually it will generate and transmit back an HTML file, which encapsulates the output of the network command in the HTML code of the looking glass web page. So again, Periscope is responsible for extracting the useful bits and for encoding them in a machine-readable JSON representation that is returned back to the user. So we can see that Periscope abstracts all the complexities and the details of looking glass interfaces, and the user can focus only on the measurement logic. But to implement this workflow, we have to tackle a series of challenges. So first of all, Periscope needs to understand the semantics of the disparate looking glass interfaces in order to map the API requests to the format understood by each looking glass. And this cannot happen manually because, first of all, there are many looking glasses, so it would be impractical. And this is a process that needs to happen frequently in order to make sure that we maintain an up-to-date list of supported looking glasses and avoid attrition over time. Another key requirement for Periscope is to support multiple users and offer them the same rate limitations that they would experience if they queried looking glasses directly and not through Periscope. And we also want to implement necessary measurement intelligence in order to maximize the number of satisfied queries within the given restrictive querying budgets. So to address the first two challenges, namely the automatic interpretation of the semantics of the interfaces and the automatic ingestion of looking glasses, we have designed a process that is based on web mining and domain-specific knowledge. we first collect a large number of URLs that potentially point to looking glasses from public web sources, such as SpearingDB or traceroute.org. And because these sources often include stale or inaccurate information, we have a web crawler that visits each URL and tries to filter out those that reply with HTTP errors or those that do not have a looking glass form. They may be other web pages that are irrelevant. And also we try to exclude looking glasses that explicitly prohibit the use of automated scripts by detecting certain keywords or phrases in the interfaces. So overall, only about 65% of the collected URLs point to a healthy, responsive looking glass. And these are the ones that we use in Periscope. And the rest ones are excluded from the ingestion process. So the next step is to try and figure out what each input element in the extracted HTML forms does in order to do the automatic mapping between API requests and HTTP calls that Looking Glasses understands. And the key intuition here is that Looking Glasses are not completely custom built in most of the cases, but they are based on some open source implementations. So we compile a list of open source templates that are used by Looking Glass operators, and we try to match the extracted web forms against these templates in order to understand the semantics of the input elements. So in 85% of the cases, we are able to find a match. So for these cases, we generate automatically the specification of Looking Glasses that we use to translate the API request to the Looking Glass specific request. And for the 15% of the cases that require manual inspection, usually we skip it, unless it is a Looking Glass that we really want to include in the system. And in some cases, we may want to include some Looking Glasses that are in regions not adequately covered, like Latin America or Africa. So we may do it occasionally, but most of the times we ignore these cases. Lastly, we have a health checker that issues periodic test queries to test the validity of the generated Looking Glass specifications. And this health checker alerts us whenever something changes in order to fit the URL back to the ingestion process and repeat it. So this ingestion process is the basis of the Periscope architecture. The output is used by a query interpreter in order to construct the queries expected by Looking Glasses. The query interpreter forwards the native queries to an HTTP client that is responsible for communicating directly with the Looking Glasses. And the HTTP client forwards back to the query interpreter the responses from the Looking Glasses so that they are converted to the machine-readable JSON representation that we return to the user. So this architecture satisfies the first critical aspect of Periscope, which is having a uniform interface between users and Looking Glasses, but it does not satisfy the request for enforcing rate limitations. So we extend the Periscope architecture to include two new modules that enable the enforcement of rate limits. So now, when a user submits a query, it will not be executed directly, but it will be queued in a database as a pending job. And we have a centralized controller that has a global view of all the system resources and all the submitted measurement requests, ongoing, pending, and completed. And the controller decides when to release a query in order to comply with the desired rate limits. So the controller follows two limits to throttle the number of queries submitted to the Looking Glasses. there is a user-specific limit that defines how many queries a user can send to a certain looking glass over a time period, and a looking glass specific query that defines how many queries a looking glass can execute over a time period, and this is global for all the users. And we have this second limit because we want to ensure that even in the case where Periscope becomes very popular and it has a lot of connected users, the underlay looking glasses will not experience an overwhelming amount of queries. So a query will be released to a looking glass only when neither of these limits is exceeded. Otherwise, it will be queued until the timeouts expire. And whenever the controller observes that the looking glasses respond with error messages, it will back off exponentially until the error messages stop or until the queue empties. So that way the controller can react to changes in the rate limits. Now, a problem is that looking glasses do not have a consistent way of communicating these rate limits. Occasionally, some looking glasses may explicitly mention these rate limits or implicitly communicate them through error messages, but there is no consistency there. So the process of deriving these limits is largely empirical, and this is a point that we would really value your feedback because it would allow us to fine-tune these rate limits and make them correspond better to the actual capabilities of looking glasses. Right now, we are very conservative to be on the safe side, so we use probably slower rates than what are supported by the looking glasses. So now we have a mechanism to throttle the user requests and avoid abuse. But we have a new problem. Now we are unfair to the users because if we put multiple users behind the same looking glass client, the underlay looking glasses will perceive them as a single user and they will enforce the query rates for a single user. So essentially, we introduce a bottleneck for the users. And to alleviate this bottleneck, we need a multi-client Periscope architecture that will use a different HTTP client for each Periscope user. And each HTTP client needs its own publicly addressable IP, which the looking glass will use to identify as a separate user. So we revisit again the Periscope architecture, and in the existing format, we deploy the looking glass clients inside a cloud platform, which allows us to scale the number of looking glass clients up and down depending on the number of connected users. So the controller is not only responsible for the timing of the query execution, but also for which looking glass client will execute a query, whether we need to start more looking glass clients or whether we need to stop some of them because users left and so on. And the looking glass clients get taken IP address from the cloud operator's address space. So the looking glasses will observe the same number of HTTP clients as the number of users connected in Periscope. Apart from that, the same query limits are enforced, but now we have the same number of HTTP clients and Periscope users. So as I mentioned in the beginning of this talk, Periscope tries to be transparent, and we try to make it clear that a request is submitted through Periscope. So with every request, we set 3 custom HTTP headers. The first header signals the fact that a request is executed through Periscope. The second encodes the IP address of the Periscope user. And the third encodes the environment that hosts the HTTP client. That can be either Google Cloud or AWS. And in the future, we may add a third flag here because we investigate the potential of hosting some Looking Glass clients in Arc probes. We also configure the IP addresses used by the HTTP clients with the appropriate reverse DNS records, so it can be easy to identify Periscope requests even when the Looking Glass deployments do not check the HTTP headers. Also, we try to maintain the same user accountability that we have with native Looking Glass querying, and for this reason, Periscope allocates a static Looking Glass client for every user with a static IP address that remains the same across the lifetime of a user in the Periscope platform. So like that, we can identify a user across different measurements. If somehow a user manages to violate some terms of Looking Glass usage, blocking a specific IP address is the same as blocking it in native Looking Glass query, which means that only the specific user will be affected and no other Periscope user will experience a change in the way they use Looking Glasses or the Periscope platform. Also, we maintain historical logs for all the user activity, so if there are any complaints, we can trace them back to the responsible users. Okay, so far I explained how Periscope interacts with the users and the Looking Glasses to facilitate queries and to regulate access. Now let's see the capabilities of the Periscope Looking Glasses. So here we see the geographical footprint of the Looking Glasses supported by Periscope. Right now we have over 570 Looking Glasses that offer almost 3,000 vantage points in 77 countries and almost 500 cities. So I believe right now it is one of the most extensive and distributed platforms that are available for public access. To geolocate the Looking Glass monitors, we relied on the location encoded on the Looking Glass interfaces. And if this location was not available, we tried to geolocate the source IP address. And we followed the same approach to find the AS number of the Looking Glass whenever it was not encoded directly in the interface. And here we see that the Looking Glasses that are supported by Periscope offer a diverse set of networking commands. Over 75% of them support both BGP and traceroute queries, and over 60% of them support both IPv4 and IPv6 queries. We also wanted to examine what portion of the internet topology is visible only through the Periscope Looking Glasses. And this is tricky exactly because we have these rate limitations in the number of queries that we can submit. So it's not possible to scan the entire routing table. Instead, we select 2,000 IP addresses randomly, and we execute trace routes to these IP addresses from all the available Looking Glasses and from all the available Arc probes and from all the available iPadLas probes. For iPadLas, we used an account with elevated quota in order to execute these measurements. So it's not the default probing quota that are more restrictive, but it has elevated privileges. And we can see that Periscope observes about 70% ASs that are not visible in the paths collected through the other platforms, and 20% of AS links that are not visible in the paths obtained from the other platforms. And although these numbers should not be taken at face value, they indeed provide evidence that the topology collected through Periscope is largely complementary to the other platforms. So by combining different platforms, we can extend the observable internet topology, and also we can extend the type of ASs that we observe, because as you see here, the looking glasses tend to capture more peripheral autonomous systems with smaller customer cones, while Atlas and ARC tend to capture ASs with higher customer cones. So by combining all the different measurement platforms, we can achieve a more diverse set of paths, which illustrates basically the benefit of using Periscope on top of the other available platforms. Another benefit, as I mentioned in the beginning, is that we can achieve more intelligent distribution of the query load across looking glasses, because Periscope has a bird's eye view of the queries executed across all the looking glasses. So it can decide how to distribute the measurements in such a way that it can maximize the number of satisfied queries without exceeding the querying quota. And the key intuition here is that some looking glasses experience higher load. For example, looking glasses in large transit providers receive more queries than looking glasses in small ASs. But some queries can be satisfied by multiple looking glasses. So for instance, if we want to know the path between level 3 and Cloudflare, we can either ask the level 3 looking glass, which generally receives a lot of queries, or we can ask a looking glass in the downstream path of level 3, which tends to receive less queries. So by taking into consideration the overlap in the use paths, we can achieve a more balanced distribution of the query load. So here we see an example of two looking glasses, level 3 and the customer level 3. The paths to Cloudflare are exactly the same after the first hop, and also the community strings are the same, which illustrates my point, basically, that we can execute the same query from different looking glasses and get the same answer. So we try to optimize the utility of the Periscope platform by selecting the looking glass with the lowest query load in order to satisfy queries that can be answered by multiple looking glasses, and to learn which looking glasses use the same paths to reach a certain destination. We rely on historical measurements and on the CADA AS relationship dataset, which gives us the customer cones. We also use historical measurements from third-party platforms like Ripe Atlas and BGP Stream in order to construct a more extensive corpus of historical measurements and improve our accuracy. And overall, we are able to increase the number of satisfied queries by 4 times for the same query budget compared to just naively executing the received measurement requests. We can also reduce the number of redundant queries, exactly because we know the queries across users. So in many cases, users probe the same IP addresses in order to troubleshoot connectivity issues. There are many of sources on the internet where users ask for a specific IP address to probe in order to see if they are connected or not. And Periscope can bundle together queries to the same addresses and execute them through a single query in order to reduce the number of queries that are experienced by looking glasses. Also, by capturing and making publicly available the measurements, we give the opportunity to the users to consume already completed measurements instead of asking for new ones. So now let's see some case studies that illustrate how Periscope can improve our monitoring and troubleshooting capabilities. The first case study is Artemis, which is a novel system for detecting and mitigating prefix hijacks. Artemis achieves very timely detection in less than 1 minute from the time the hijack starts. And to do that, it combines passive BGP collectors with Periscope. And when they include Periscope in the detection methodology, they achieve a faster detection in 60% of the cases, which at first may appear counterintuitive because Periscope supports only low-frequency queries, but it has a higher variety in the vantage points with known locations and known connectivity. So although it supports only slow probing, it allows more targeted and fine-grained queries that can improve the detection speed significantly. And this is exactly what we wanted to achieve. So we didn't want to bypass the query rates and issue more queries than supported. We just wanted to facilitate the execution of queries across the available looking glasses. The second case study is NetDiagnoser, which troubleshoots network disruptions. So NetDiagnoser basically constructs topologies by running distributed trace routes and tries to localize the AES that is responsible for the disruption. However, if it encounters unresponsive hops or private IP addresses, it may not be able to spot the AES is responsible for unreachabilities. And to solve this problem, it combines BGP and traceroute measurements from the same routers, basically, which is possible only through looking glasses. In their implementation, they didn't have the way to execute this methodology, so they were limited in simulations. But with Periscope, now we have the ability to implement this methodology in practice and detect such failures and localize them. So the current status is that Periscope is accessible after email request. We try to be a bit conservative at the moment regarding the requests that we satisfy. We ask for a detailed description of the way Periscope will be used and the projects in order to maintain the control of the Periscope resources. We provide detailed API documentation and we explain all the details on how to execute and consume queries. And right now we're working on developing a graphical user interface and on hosting looking glass clients inside ARC measurements in an effort to reduce basically the cost of the whole system, because the use of cloud platforms provides a lot of flexibility, but it carries a very high cost. So I want now to underline that we need your contributions and your feedback in this project, especially if your network runs looking glasses. There are 3 variables that will be most useful to us. First of all, the per user query limits. the global query limits that are supported by Looking Glasses, and whether you want to opt in or opt out from the Periscope project. So currently, Looking Glasses are by default in opt-in mode unless they specifically prohibit the use of automated tools. So you can contact us at periscope-info@kda.org and let us know your feedback. Also, we would value utilization statistics and historical data if you maintain them. And ideally, we would like support with the infrastructure. As I said, cloud resources can be very costly, so we would appreciate if you can share some VM instances or cloud computing credits. So to conclude, Periscope tries to unify Looking Glasses under a standardized uniform API. It enforces per user and per Looking Glass rate limits to prevent abuse, and it provides transparency and accountability for the queries that are executed through each platform. And it combines a number of benefits that can be summarized as offering an extensive topology coverage, optimization of utilization of Looking Glass resources, and the improvement of our troubleshooting and monitoring capability. Thank you very much.
Question for you, Don Lasher, F5. Have you considered any sort of a subscription model or donation model to help fund continued research?
We don't have a formal model at the moment, but anybody can contact us. We will, really appreciate it.
Matt Petak, Yahoo. You mentioned holding on to or caching LG query results to reduce load on the LGs. How do you indicate how fresh or stale the results are to someone doing a query through Periscope?
Okay, that's a good question. So it's a bit complicated, and we have a paper that explains it, but we learn basically from historical measurements which routes tend to change often and which routes tend to remain stable. And through a learning process using historical data combined from different platforms and different views, we infer the stability of and the staleness basically of archived measurements.
I'm going to repeat a quote that's often used in conjunction with the stock market. Past performance is no guarantee of future results. Very often when you're most curious looking at a looking glass, it's something is very different than it has been for the past many months. And so saying, well, that's been true. Stable for a long, long time. We can cache results.
When I mean caching, I don't mean for very long period. I mean for very short periods. And basically what happens is that redundant queries happen all together, possibly in the same hour, because there is some routing incident and all the users flock to query the Looking Glass with the same destinations. So the caching is useful for short time periods, not for paths collected before month.
I would recommend you have like a last modified header or some piece of information that the querier can observe to see this is a current result or this result is X minutes old, so they can decide if it's accurate enough for their uses. But this looks really good. Thank you.
Thank you, Vasilius.
Hi, Julian Goodwin, Google. What sort of broken route servers have you encountered? I found one just a couple of weeks ago that claimed to support v6, but input validation wouldn't allow a v6 address to be entered.
Sorry, can you repeat?
What sort of broken looking glasses have you encountered? Those that claim to work or support features but fail in interesting ways.
I'm sorry, can you repeat the question? We have trouble hearing.
What sort of broken looking glasses have you encountered, and what sort of ways have they failed?
What sort of looking glasses? Ah, broken. Basically, there are all sorts. So some looking glasses are just in ASs that changed organization. So they were so the new organization removed them. Some looking glasses appear just to be offline or to be unable to connect to the routers. So they appear as alive, but they are not in reality, or they do not have any routes. So basically, it's one of the problems that the available public sources of looking glass data are not updated frequently, and as a result, they contain a lot of stale information.
Okay, thank you again, Vasilios.
Thanks.